next speaker is also from NCTS. From Chris Lau, right?
Yes.
Dr. Lau. Start.
Okay. Yeah, sorry about the technical problem. So today I'll talk about this work together with Chenda at the back, and then Jeff and Masaki. And the paper is published in Thesis Letter B. So this work is about the relationship between randomness and chaos. So we would like to study whether they are related or what are the relationship between chaos and this random, using some simple models that we look at, which are the Qubit models. So classically, chaotic system has been around or has been studied for a very long time, both mathematically and physically. So these are some examples of chaotic system. So this is double rod pendulum. So if we attach two balls together and then observe the trajectory of this system, then we know it's chaotic. And also in a much larger scale for climate or weather, it's still due to the nonlinearity of the physical equations, and it's very hard to predict what will happen in the future. And in classical chaos, one of the condition, or one of the more easy to understand condition, is that if we perturb the initial condition a little bit, and at later time t, the deviation grows at exponentially quickly. And this is one of the signature of a chaotic system. But what about quantum chaos? So since we know all the classical system arises from quantum theory, so if we start with quantum theory and take certain limit, for example, in the large quantum number limit, then we cover the classical system. But since we know quantum theory are all governed by Schrödinger equation, which is linear, so how could a linear quantum system give rise to something that's nonlinear? So there has been quite a few quantities that people try to use to understand quantum chaos. These two are the more, or these two types of quantities are the most used in the study of quantum chaos. One is called the out-of-time ordered correlators, and it's shortened as OTOC. And then the other is the use of random matrix theory, which is the study of the statistics of the quantum theory. And within this framework, we can look at the spectral form factor and then also the level spacing distributions and see whether the system can be is chaotic or not. So in this talk, we'll focus on the random matrix theory side and look at the spectral form factor, and also briefly mention how the level spacing distributions looks like for a chaotic system. And we'll see whether these two are good quantity to quantify chaos. So here is just a quick review of what is the first quantity that I mentioned before, which is the OTOC. So the OTOC is defined to be the commutator squares of some operator, one at time t and one at time 0. And if we take the thermal average of these operators, if the theory is chaotic, then it's a growth like e to the some power of t. And it's easier to see why this quantity is a good measure of chaos. If we just look at quantum mechanical system with operator x and p, the commutator of these x at time t and p at time 0 will just give us some variation of x at t over variation of x at 0, which is exactly the same condition that we have in the classical systems. So this inspired us to use this type of correlator to study quantum chaos, because now this is in the operator form. And back in 2016, in the quantum system, they managed to show that there exists certain bound of this quantum chaos. And you see there's an h bar in here, so this is strictly quantum. And the focus of this talk is this random matrix theory. Since in quantum theory, all the quantities that we compute are expectation value of some operators, which means this is like a probabilistic way of computing physical quantities. And that means we are sampling the statistical properties of some systems. And back in 1955, in this paper, Eugene Wigner proposed a way to study the spectrum of some heavy nuclei with many protons and many neutrons. And with this many number of particles, and this system is a many-body system. And when we look at the eigenstate, there should be many states for these many-body systems. And in order to extract properties out of this very complicated many-body system, he proposed that we can use random matrix theory to study the spectrum of the nuclei. Instead of looking at individual eigenstate of this many-body system, we can just look at the overall statistical properties. And this is the kind of one of the first uses of random matrix theory. So how do we connect random matrix theory to quantum chaos? The way, one of the first idea was invented by Jakob Sinai. I'm not sure if I pronounced the name correctly, but yeah. So he proposed a billiard system like this, and he proved that in this classical system, when you look at the phase space, no matter where you start, you sample all the phase space in the system. And that means this synapse billiard is a chaotic system, at least classically. And we can convert this system into a quantum version, which is just putting an infinite potential wall at the side and then also at the center, a circular infinitely potential wall. And if we solve for the spectrum of this quantum system and look at the spectrum, it is observed that the spectrum follows the random matrix theory behavior, which means by having in a quantum system, if you look at the spectrum and it follows random matrix theory the classical version of this system is chaotic. So this is how we start inspire us to use random matrix theory to study chaotic system or to study quantum chaos.
Can I ask a very stupid question? Sorry,
yes.
I'm very unfamiliar with this.
Yeah.
It's important to have the central pillar for it to be chaotic, right?
You mean
if I remove it, then it can you have
if it's just a square, then
yeah.
it's not
So is there like a tunable thing that I can tune the radius of that pillar such that you transition between?
Yeah, I think so there's some ratio between the radius of this and the box size.
Okay.
I can't remember exactly, but I think in Hashimoto's paper they also talked about this. So, but there's some ratio which if the size is too small, then you don't know that.
So is there like some critical phenomenon that you go transition from being into chaotic, that once there's a critical value for that ratio?
Yeah. If I remember correctly, then I cannot recall it from my head. But yeah, if you want to know more, please refer.
Okay.
Can we do analytical?
And this one,
Boundary condition
the boundary, if you solve it numerically, and then you can collect all the eigenstates, and then you can.
In the geometry of this boundary necessary square, or can be.
I think that you can deform the boundary to be like an elongated. So you have two half circle and then link them together. That is also chaotic. Yeah. So in their paper, they study many different types of these immediate systems. Yeah. But they only look at OTOC, but not the spectral form factor. So within the framework of random matrix theory, I mentioned that there's one quantity that you can compute, which is the spectral form factor here, which is just defined to be the ratio of some complex temperature or this form, set beta and t, squared divided by setting the t equal to 0. And this is a typical behavior of this spectral form factor for chaotic systems. So the special features come from the second half of this plot. So after the decay of the correlation between different eigenstates, then due to the chaotic behavior, then there will be an increase in correlation and then it flattens out at some point. So here, this kind of figures would be an indicator of chaotic behavior, and we are going to test whether this is a good measure of chaotic system. So the Qubit model that we are interested in is called the SYK model, and the Hamiltonian is given by this form for general Q. So Q indicates how many Q point interactions we have in the Hamiltonian. And we restrict ourselves to Majorana fermions with this anti-commutation relations. And the coupling here, JI1 to IQ, is a sample from some Gaussian distribution with these variance. With Q equals to 4, and at large n, people can solve analytically that this system is chaotic. So, but we would like to look at an even simpler system than the Q equal to 4. So this is the model that we study in our paper, which is Q equal to 2. So this is it's simply a binomial in fermions in the Hamiltonians. And this is the probabilistic, the distribution, the Gaussian distribution that we sample our coupling constant from. So this is the simple form of the Hamiltonian. Since we know it is bilinear in fermions, so it can be exactly integrated out in the path integral. So this system is integrable, which is supposed to be non-chaotic. But then if we look at what we believe to be a good measure of how chaotic the system is, such as looking at the spectral form factor, we will observe something interesting. So on the left-hand side is the SYK2 model that I mentioned just in the previous slides, and this is the result from SYK4. And this graph is taken from this paper. So if you compute the spectral form factor for SYK4, you see this recovers exactly like I mentioned before for the random matrix theory. So if you look at the spectral form factor, there is a decrease in the correlation between eigenstate, and then there's a linear increase and then it flattens out. So it fits in with understanding that SYK4 is chaotic from analytical results. But if we, on the other hand, for integrable system like SYK2, and if we compute the spectral form factor, we repeat all the calculation, extract the eigenstate, and look at the spectral form factor, we see that it behaves exactly the same as the chaotic SYK4. So it's kind of confusing, like for integrable system, which is not supposed to be chaotic, and if you look at the spectral form factor, it still gives us exactly the same behavior. So either the spectral form factor is not a very good measure, or it's not the unique condition of a chaotic system, or there's something wrong with this SYK2. And we can also check the level spacing of the SYK2 to see whether the random matrix theory is really a good measure of chaotic system. So here I plotted a few curves here. So this curve is the Poisson distributions of the level spacing, and then this one is the Wigner distribution. So according to the random matrix theory, or according to what we believe to be true, if the spectrum or if the level spacing distribution of certain of the physical system follows the Wigner distribution, then it's supposed to be chaotic. And from here we see that, so these three are all the level spacing distribution that you can compute for 6 Majorana fermions in SYK2. And you see that they all follows the Wigner distribution. So if random matrix theory gives a very good indicator of chaotic system, that means SYK2 should be chaotic. But we know this can't be true. So there's some contradiction in here. But if we look into more details and see what's going on, for example, if we reduce the number to n equals to 2, which can be exactly solvable analytically, then we see that for this particular system, sorry about the quality of these figures. So these are two sets of spectral form factor for both n equals to 2 and n equals to 4. So this part is the n equals to 4 behavior. So down to n equals to 4, we still kind of see the expected behavior of a chaotic system, which is first decrease, increase, and then it flattens out. But while it's only when we go down to n equals to 2, it's simply just a decay and it just flattens out. So there's no more linear increase in the systems. And from this, we can, we can solve n equals to 2 system exactly. We know that the only difference between n equals to 2 and other larger number of fermions is that the eigenfactors of n equals to 2 system is independent of the coupling constant. And it seems to indicate that this behavior in the spectral form factor comes from the dependence of comes from the eigenfactor depending on the coupling constant of your systems. So if your eigenfactor is independent of the coupling, you'll never get that behavior in the spectral form factor. So that means if the spectral form factor is only an indicator that it suggests that spectral form factor is only an indicator that our eigenvectors contain or depends on the random coupling of the system. So if it goes down to some very simple, exactly solvable system like n equals to 2, then we no longer obtain that structures in the spectral form factor. So it kind of suggests to us that, or we would like to suggest that spectral form factor is not unique or is not an efficient indicator of chaotic system, but rather it simply means that if we have a set of eigenvector depending on on the coupling constant, and it will generate the behavior that you observe.
I think we want to play more. We want to say the random matrix is not enough to diagnose chaos.
Yeah, okay. Yeah, thank you for adding to that.
It's better than space one.
Yeah, thank you. And then we also try to check this computation using other models, and they all give a consistent result. So we check it using, for example, transverse Ising models, and then that still gives us the same behavior where if the eigenvectors are independent of the coupling constant, we don't get the expected spectral form factor behavior. And it might be true that it might be true that for a general integrable system that follow this structure. And I think I'll just stop here. Thank you very much.
We already discussed. Okay, let's speak again and then we'll come to the next one.